Now for the step 2, for determining a standard expression from a truth table, convert each binary value to the corresponding product term by replacing each one with the corresponding variable complement and each zero with the corresponding variable. And it will be much easier when we discuss with an example. Suppose the expression where there is a zero in the output is 1001. So I will write it like that. 1 is represented by variable complement, 0 is represented by the variable itself in a true value, and it is a bar plus b plus c plus d bar. Now let us take an example. Suppose we are given a truth table with input a, b, c and the output x. We have some zeros in the output, we have some ones in the output, and with the 3 input variable we have overall 8 binary combination. 4 values are 1 at the output and 4 values are 0 at the output. So where there is 1, this is a SOP. Where there is a 0, this is a POS. So directly we can write down the values of SOP and POS in the standard form looking into the truth table. So sorry. So there are 4 ones in the output and the corresponding binary values of the 1 are 0, 1, 1, 1, 0, 0, 1, 1, 0 and 1, 1, 1. So 0, 1, 1 is nothing but A bar B C. 1, 0, 0 is A B bar C bar. 1, 1, 0 is A B C bar and 1, 1, 1 is A B C. So we combine all these product term into the sum and we get SOP as X equals to A bar B C plus A B bar C bar plus A B C bar plus A B C. So where there is 0, this is POS. So again we have 4 zeros which have the corresponding values as 0, 0, 0, 0, 0, 1, 0, 1, 0 and 1, 0, 1. And we can write out the corresponding value for 0, 0, 0. It is A plus B plus C. Next 0, 0, 1 is A plus B plus C bar. 0, 1, 0 is A plus B bar plus C. 1, 0, 1 is A bar plus B plus C bar. So this is the way how we can find out the values of SOP and POS from the given truth table. Now, the next and very much important topic is your Karnaugh map. Now onwards, so whatever you design, starting from your combination logic until the end of this syllabus, each time you have to use this K-map, and the K-map is used for the simplification of the Boolean functions. So far, we have simplified the Boolean expression with the help of Boolean algebra, and many times when the expression is lengthy, it is very tough to solve the Boolean function with the help of Boolean algebra, and in that case we use the Karnaugh map. It feels a little difficult using Boolean algebra laws, rules and theorems to simplify logics. A K-map provides a systematic method for simplifying Boolean expression, and if properly used will produce the simplest SOP or POS expression possible, known as minimum expression. It's pretty much similar to the truth table. Instead of being organized input and output into columns and rows, the K-map is an array of cells in which each cell represents a binary value of the input variable. The cells are arranged in a way so that simplification of a given expression is simply a matter of properly grouping the cells. K-maps can be used for expressions with 2, 3, 4, and 5 variables. Beyond 5 variables, it becomes pretty much difficult to solve with the help of K-map. Then we have a tabulation algorithm, which we are going to discuss after the K-map. Now, in our discussions which is coming on, we are using 3 and 4 variable K-map to discuss to be discussed to illustrate the principles, how it is used and how the groupings are made. We can look into the how the 3 variable K-map looks like. Suppose we have it is oh sorry, this is wrongly written. It is X, Y, and Z. These are the 3 inputs. Then we put the binary value of the input 0, 0, 0, 1, 1, 1, and 1, 0. Keep in mind the sequence will be same. In the X moving from in the this particular column 0 and 1. This row, for this particular row, X is common 0. For this particular row, X is common 1. For this column, the value of Y and Z will be 0, 0. So when we come to the min term, the X is 0, Y is 0, and Z is 0. So I write the term X bar, Y bar, Z bar. That is the sum of products. So sum of product is X bar, Y bar, Z bar, because the value of X is 0 in this particular, this is some kind of matrix. Y is 0 and Z is 0. And this is represented by the min term M0. For the next expression, we have X is 0, Y is 0, and Z is 1. So we write X bar, Y bar, Z. That is 0, 0, 1. So min term is 1, M1. For the next value, adjacent value, we have X 0, Y is 1, Z is 1. So the expression comes to be X bar, Y, Z. So it is 0, 1, 1. So 0 comes from here, 1, 1 comes here. So 0, 1, 1 is 3. Now the min term is M3. And the next expression, we have 0, X is 0, Y is 1, Z is 0. So it comes to be X bar, Y, Z bar. That is 0, 1, 0. 2, min term is M2. Similarly, for when X is 1, it is 1, 0, 0, 1, 0, 1, 1, 1, 1, and 1, 1, 0. So these are the representations by the min terms M0, M1, M3, M2, M4, M5, M6, and M7. So this is the way how a K3 variable K-map looks like. So there are almost 8 cells. Each cell represents a possible distinct input variable combination. Now this is a 4 variable K-map. We have 4 input variables X, W, X, Y, Z. These are the input variables. It may be A, B, C, D. So whatever is the representation of your variable, you can write it like this. Again, we have in the rows 0, 0, 0, 1, 1, 1, 1, 0. You can say that these codes are written in gray code, so that at one time one bit is changed when we are moving from one step to the another one cell to the another cell. Again, in the X, as we have 4 in the column, we have 2 input variables. Then again it is 0, 0, 0, 1, 1, 1, and 1, 0. So with the 4 input variables, we have 16 distinct combinations. Suppose this cell, when you talk about this cell, so here W is 0, X is 0, Y is 0, and Z is 1. So the value will be W bar, X bar, Y bar, Z, that is 0, 0, 0, 1, that is M1. So this is your M1. You can directly map M1 here. Now when we talk about this particular cell, so here W is 1, X is 1, Y is 1, Z is 1. So the value will be W, X, Y, Z. That is 1, 1, 1, 1, 15. And the corresponding min term will be M15. You can look into the any cell that the binary value will be representing the min terms. And for let us example take this. W is 1, X is 0, Y is 1, Z is 0. So the value will be W, X bar, Y, Z bar. It is 1, 0, 1, 0. That is 10. So the corresponding min term is M10. So in this way, first of all, when you are giving a K-map, find out when you are giving, you have to solve a Boolean function with the help of the K-map. First of all, identify in number of inputs or number of input variable. Convert if there are 4 variable, make a K-map like this and put the values. Now the cell adjacency, how the adjacent cells are identified, you can see with the green cells. These are the adjacent cells. In the you have in the horizontal way adjacent cell, you have in the vertical way the adjacent cells. Adjacent cell may be like this cell and this cell. These are also adjacent cell. This is an adjacent cell. This cell and this cell. These cells may be adjacent like this. When we can fold the K-map. So it is just like a mat, and when we fold the mat in the rounded way, then the whichever cell are next to each other, these are called adjacent cell. So every time when we are going to discuss some example, it is pretty much it must be pretty much clear in your mind that which are the adjacent cells and how we have to combine one adjacent cell to the another, and how we have to make pair, make quad, make octet, like this. So in the next lecture, we'll discuss the K-map SOP minimization. And till now, if you have any difficulty, just take a look on the K-map and how it is represented. And in the next lecture, we'll discuss the how to use the K-map for the minimization of SOP.